So for the last of our finding the probability of making a type 2 error, we are going to have a look at binomial. So again, we are going to look at some where we are given the accept or reject region, and we're going to look at some where we are given the significance level. So for the first example, we have less than half of the flowers in a packet are meant to be blue. So that means that H0 is going to be that P is 0.5, and H1 would have been that P was less than 0.5 if we were to perform a hypothesis test on this. So we have a random sample of 10 flowers which are planted. That's meant to say and. The colour that they blossom is recorded. It is decided that if less than 3 flowers are blue, then the probability of the packet is correct. So here we're using X follows binomial distribution of 10, 0.5 to begin with, and we're told that we are going to be accepting, less than, so this is the reject one. So this is rejecting H0 if X is less than 3. So remember that we actually want the accept H0 region, because the type 2 error is that H0 is not true, but we accept H0. So that means that we would accept H0 if X was greater than or equal to 3. It actually turns out that it's a typo and only 40% of the flowers are meant to be blue. So we're changing our H1. Our H1 is actually that P is 0.4. So that means that when we're finding the probability of making a type 2 error, we are going to be finding the accept H0 region, but using X squiggle B 10, 0.4. So in our calculator, we're going to go to dist binomial BCD. Our lower is 3, our upper is 10. The number of trials we have is 10, and the probability is 0.4. And that gives us a beta of 0.833. Notice here that if you have the older version of the calculator, instead we are going to have to do 1 minus the probability of X being less than or equal to 2, where your X would be 2, your number of trials would be 10, and your probability would be 0.4. And that should give you the same value for beta. For our second example, we've got the pass rate on an exam is meant to be more than 40%. So our H0 is that P is 40%. Our H1, if we were doing a hypothesis test on this, is that P would be more than 40%. Again, we've got a sample of 10 people taken, and it's decided if more than 7 of them pass, then they are correct. So that means that we are rejecting H0 when X is 7 or more, so greater than or equal to 7. So that means that we would be accepting H0, which we need for a type 2 error, when X is less than or equal to 6, and we're told that the pass rate for the exam is actually 60%. So our H1 is actually that P is 0.6. So we're going to be using X follows the binomial distribution with an n of 10 and a probability of 0.6, and we're going to find the probability that we have less than or equal to 6. So our lower is 0, our upper is 6, we have 10 people that we're looking at, and our probability, because H0 is not true, so that means that our true probability must be the one that we're using, gives us a beta of 0.618. For the next example, we have a coin is thought to be unbiased, which means that it's not going to be a half. So the coin, unbiased means that it's going to be 50% each time. So that means that our H0 is that it is unbiased, so it is a half. And our H1 is that it's going to be biased, so not a half. The coin is thrown 10 times, And if we get between 2 and 8 heads are counted, then it is decided that the coin is unbiased. So because that's saying then that the probability is 0.5, that's our accept H0 region. That's what we want. So we're accepting H0 when 2 is less than X is less than 8. And again, as we talked about when we were looking at Poisson, because it just says between 2 and 8 and it doesn't say inclusively, generally that means that we're meaning strictly more than 2 and strictly less than 8, which means that actually it's going to be easier if I rewrite this as 3 is less than or equal to X is less than or equal to 7. And if you struggle with that conversion, then if we did a quick number line, we're saying more than 2 and less than 8, and then you can see that it's 3 is less than or equal to X is less than or equal to 7 from there. We're also told in the question that the true probability attained ahead is 40%. So our H1 is no longer that it's not 0.5, instead it's that it's 40%. So we're going to be using X follows the binomial distribution with the number of trials of 10 and a probability of 0.4, and we're finding this probability. If you have the new calculator, then your lower is 3, your upper is 7, your number of trials is 10, and your P is 0.4. That gives us a probability, our beta, of 0.820. Just worth pointing out again that if you have the old version of the calculator, you're going to have to do the probability of X being less than or equal to 7, take away the probability of X being less than or equal to 2. So the biggest one that we want minus the biggest one that we don't want. So for all of those ones that we've looked at so far, we've been given either the accept region or the reject region. We just have to make sure that we read it carefully to see which one we've been given. We're now going to look at how we handle this if we're given the significance level instead. And it's going to be a similar way to what we did with the Poisson ones, which is that we're going to have to find the region. We're going to have to find the critical value so that then we can find our accept H0 region. So Johnny wants to perform a hypothesis test at a 10% significance level to determine if the probability of randomly selecting a tulip growing is 60%. Johnny plants 20 tulips, and counts how many of them grow. It is found that actually the probability of growing a tulip is 70%. Find the power, find the probability of making a type 2 error for the hypothesis test that Johnny performed. So here it's a two-tailed test because Johnny wants to perform a hypothesis test at a 10% significance level to see if a randomly selected tulip growing is 60%. So it either is 60% or it's not 60%. So our H0 would have been that the probability was 60%, and our H1 would have been that the probability was not 60%. We are planting 20 tulips, so we're starting off by using X follows the binomial distribution with an N of 20 and a probability of 0.6. And as we talked about when we were looking at Poisson, this is two-tailed, so I'm wanting to find the value below and the value above. That means that I have a maximum of 5%, because I'm having to split my 10%, 5% on the lower part and 5% on my upper part here. So to start off with, we're just going to try some numbers, see where we get. So we're going to have 0 as our lower. We're going to be changing our upper. We've got the number of trials is 20 and the probability is 0.6. It's a good idea to have a think about what the mean value is going to be. So if we had 20 times 0.6, then that gives us 1.2 for our, 12 for our mean. And so that tells me that the lower end of my value is definitely going to be less than 12 when I'm looking at down here, because 12 is going to be somewhere around the middle. So if I try instead, let's try 8. Let's look at less than or equal to 8. So the probability that x is less than or equal to 8 gave me 0.0565. So that was quite a good guess to start off with. That isn't small enough though, so I need to try a smaller number. So instead, we're going to try less than or equal to 7, which gives me the probability of x being less than or equal to 7, gave me 0.0210. So that is my lower critical value, which means that anything less than that's going to be in my critical region, my reject H0 region. So 7 is going to be on this side of the line and 8 is going to be on this side of the line. Looking at the top end, so again, 12 was going to be the mean. So I'm going to try a number that's bigger than 12. Let's try 15. So 15 can be my lower. We're only going up to 20, so 20 is my upper. Still the number of trials is 20 and the probability is 0.6. So the probability of x being greater than or equal to 15 gives us 0.126. So that's not a small enough area, so I'm going to have to try a bigger number. So let's try greater than or equal to 16. So, whoops, 16 is our lower this time. So that's giving me 0.0510, sorry, to 3 significant figures. Again, this isn't quite small enough, so we're going to try a bigger number. So let's try 17. So the probability of x being greater than or equal to 17 gave me 0.0160. So that is my top critical value, the first value that's in my reject H0 region. So 17 is going to be on that side of the line and 16 is going to be on that side of the line. So this part here in the middle is my accept H0 region. And that's what I need when I'm trying to find the probability of making a type 2 error. So that's 8 is less than or equal to x is less than or equal to 16. We are then told that it is found that the actual probability of a tulip growing is 70%. So we're changing our H1. Instead of it being not equal to 0.6, we are using equal to 0.7. And we're having a look at this probability of being between 8 and 16, given that we're now looking at the probability being 0.7. So what we're actually going to be using now is x follows the binomial distribution with an n of 20 and a probability of 0.7. So putting this into my calculator, the lower is 8, the upper is 16. We have 20 trials and the probability that we're using now is 0.7. And this gives me a beta of 0.892. So for our last example, we have Smith gets test questions right 40% of the time. After his teacher advises him on revision techniques, it is believed that he will get more than 40%. So if we were performing a hypothesis test with this, our H0 would be P equals 0.4 and our H1 would be that P is more than 0.4. This is investigated at a 10% significance level. The true percentage of Smith now gets it right is 50%. What is the probability of making a type 2 error? So to begin with, we are using x follows the binomial distribution with an n of whoops, we've missed out how many questions there are. So I've just altered that here so that we have a set number of trials. So we're saying that we have 25 questions. It will give you the number of trials in the question. So as I was saying, to start off with, we have that x follows the binomial distribution with an n of 25 and a probability of 0.4. This time we have a one-tail test because we're wanting this to improve to be more than 40%. So we are wanting to find this value here so that we have it was 10% significance level, so we want 10% on this side of the line. So to start off with, we have 25 questions. We have a probability of 0.4. Again, if we have a think of what the mean would be, because we definitely want to be more than the mean. So 0.4 times 25. I believe that's 10, just double checking, 0.4 times 25. That does give us 10 as our mean. So we're going to try a value that's bigger than 10. So let's start off by trying 14. So 14 is our lower, 25 is our upper. So the probability that x is greater than or equal to, what did I choose, 14, gives us 0.0778. So that is too small, so we're going to have to try a bigger number. So we've got, sorry, a smaller number. So we're going to try 13. So let's try probability of x is greater than or equal to 13. And that gave us 0.154. So that means that 13 is in our accept H0 region, but 14 is our critical value, and then that is the first value in our critical region here. So that means that we would accept H0 when x is less than or equal to 13. We are then told that the actual probability percentage that he gets right now is 50%. So now we're saying that this is 0.5. We're still looking at the 25 questions. But now we've got a probability of 0.5 and we're trying to find the probability that it's less than or equal to 13. So our lower is 0, our upper is 13, the number of questions that we have is 25, and our probability is 0.5. So that gives us a beta of 0.655. I would now like you to pause the video and give the Now You Try questions a go. So hopefully you paused the video and gave the Now You Try questions a go. For the first one here, we've got the probability that Brian Air loses a piece of luggage, is 80%. New measures are put in place and this is now thought to be reduced. So if we were doing a hypothesis test on this, our H0 would be that P was 0.8. Our H1 would be that P was less than 0.8. It then says it is decided that if 5 or less pieces of luggage out of a sample of 10 are missing, then the measure has been successful. So that is our reject H0 region, that 5 or less, so x being less than or equal to 5. And at that point we were using x follows a binomial distribution with an n of 10 and a probability of 0.8. So that means that our accept H0 region would be that x was greater than or equal to 6. However, in reality, our H1 should have been that the probability was 0.5. So then using x follows a binomial distribution with an n of 10 and a probability of 0.5, finding the probability that x is greater than or equal to 6 gives us 0.377 for our beta. For question 2, we've got, in the new Kinder Egg series, there are 4 different characters to collect. It is thought that one of the characters is more likely to be inside a Kinder Egg than the other. So that means that if we were doing a hypothesis test with this, our H0 would be that P was a quarter. Our H1 that would be that P is more than a quarter. We then have a sample of 10 Kinder Eggs. So we're using x follows a binomial distribution with an n of 10 and a probability of a quarter. And we're told that if more than 4 contain the specified toy, then it's regarded that it has a higher probability than the others of being inside. So that's our reject H0 region, that X is greater than or equal to 4, which means our accept H0 region would be less than or equal to 3. We're then told that the actual probability of that toy being inside is 40%, so our H1 should have been that the probability is 0.4. But that gives us X follows the binomial distribution with an n of 10 and a probability of 0.4. Finding the probability then that X is less than or equal to 3 gives us a beta probability of making a type 2 error of 0.382. For question 3 in the Now You tries, we've got the probability that it will rain in the first month of the summer holidays is thought to be 30%. A random sample of 10 days is selected and it is recorded whether it rains on that day. If it rains on between 3 and 5 days, then the probability is thought to be correct. So that's our accept H0 region. Well, you can see here that if, again, it doesn't say inclusively, so between 3 and 5 would be that 4 is less than or equal to X, which is less than or equal to 4, which then just leaves us with X being equal to 4. So that's our accept H0 region. It is actually found that the probability of it raining in the first month of the summer holidays is 90%. So our H1 should have been that the probability is 0.9. So we're then using, forgot to write it down, but we're using X follows the binomial distribution with an n of 10 and a probability of 0.9. And we're finding the probability that X equals 4, which gives us a beta probability making a type 2 error of 0.00138. For the next two, these two is where we are given the significance level and we're having to find that critical region, our reject region and our accept region before we can actually answer the question. So the Kelly party say that less than 30% of the voters in the recent by-election, 50 people were interviewed and it was investigated at a 10% significance level. So for that, our H0 is 0.3. Our H1 would be that the probability is less than 0.3. We're then using X follows the binomial distribution with an n of 50 and a probability of 0.3. And as you can see, because it's less than, this time we want our 10% to be on this side. So when we looked at the probability of X being less than or equal to 10, that gave us 0.0789. So that is less than 10%, but I had to make sure that was the biggest number that gave me less than 10%. When I tried 11, I got 0.139, which is more than 10%. So then you can see that 10% is my critical value. It's the biggest value in my critical region. And 11 is going to be the first value at which I accept H0. So we'd accept H0 if X was greater than or equal to 11. We're then told that the actual percentage of voters was 0.26. So then we're using X follows the binomial distribution with an n of 50 and a probability of 0.26 to find out what the probability would have been that X was greater than or equal to 11, which gave us a beta of 0.787. For this last one, we have a production line at Melfield factory produces a component for Matsui DVD players. However, faulty components are produced with a probability of 5%. The production line is upgraded. A sample of 50 components is observed. The engineer claims that they have altered the chance of a faulty component being produced. So because they just say altered, they don't say improved or decreased or increased, that means that we're looking at a two-tailed test. So that tells us that if we were doing a hypothesis test with this, our H0 would be that the probability was 0.05 and our H1 would have been that the probability was not 0.05. And then we're told that we're investigating this at a 5% significance level. So because it's a two-tailed test, we're going to cut that 5% in half. We're looking at 2.5% at the bottom end and 2.5% at the top end. We're using X follows the binomial distribution with an n of 50 and a probability of 0.05. And I first tried to find a probability at this side, which gave me less than 2.5%. When I tried less than or equal to 1, I already got 0.279, which is quite a big probability still. So then I tried the probability of x being less than or equal to 0, or just equal to 0 you could have done, and that gave me 0.769. So that tells me that actually at this bottom end, even though we have a two-tailed test, there is no value that is small enough that's going to say that it has decreased. So that means that 0 is still not in my critical region, it's still in my accept H0 region. So then for the top end, I tried greater than or equal to 5, which gave me 0.104, which is more than 2.5%. So I had to try a bigger number. So then I tried greater than or equal to 6, which gave me 0.0378, which is a smaller percentage, but it's still not smaller than 2.5%. And then when I tried greater than or equal to 7, I ended up with 0.0118, which is smaller than 2.5%. So that would be my critical value, the smallest value in my critical region at this top end, which would then mean that 6 was the biggest value at which I accept H0. So then my accept H0 region would just be that x is less than or equal to 6. Like I pointed out, there's no critical value at this end, so that means that there's no value that's small enough that would tell me that it has decreased. We're then told that the true probability a component is being faulty is now 3%. What's the probability of making a type 2 error? So then we had x follows a binomial distribution with an n of 50 and a probability of 0.03. We're finding the probability that x is less than or equal to 6, and that gives us a massive beta of 0.999. And if you think about it, that makes sense that the chance of making a type 2 error, the chance of H0 not being true, and we accept H0, is large, and part of that is because we don't have any values at the lower part of our number line that would mean that we would reject H0. And considering that actually the probability had decreased, that meant that there was no values in our hypothesis test that would mean that we could correctly reject H0 at that lower end. And so that's quite important to bear in mind if you are setting up a test and you have a look at the critical values to see where your critical region lies. If you end up doing a two-tailed test, but actually there's no values that make it so that that could be correct, then the test isn't very good, because we could have done a one-tailed test, but as you can see, the probability actually decreased. So that would mean that we would definitely end up, hopefully anyway, with the results that we get from the test, accepting H0, because we wouldn't want to say that the probability had increased, because it definitely has not increased. So that's quite an interesting one to have a look at. You can end up with this happening in an exam, but as I said, it means that the test really isn't set up correctly, because we have no values at the lower end that would mean that we could say that we were rejecting H0. So next time we're going to move on to having a look at power. We've had a look at all the different major ones that can come up with in terms of finding the probability of making a type 1 and a type 2 error. Thank you very much for listening.